Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, in today's video we are going to do coordination chemistry, one of the most important topic, that is bonding theories. Okay, so previous to this we have already completed nomenclature, isomerism, important definitions, Werner's theory, right? So today we will be covering bonding theory, in which we have two parts, valence bond theory and crystal field theory. Okay, so this is a very important topic from coordination compound, from where every year we can expect at least one question from this topic. Okay, so yes, let's get started now. One more important request, please join our WhatsApp channel. The link of the WhatsApp channel will be there in the description section. Now this is important so that you can download the notes, you can download the question paper, solutions, everything will be provided in our WhatsApp channel. Okay, so yes, now I want all of you to sit with a notebook and a pen and then make notes and practice questions with me. Okay, so we are going to do a lot of questions and we are also going to solve some previous year questions from this particular topic. Okay, so now let's get started here. So now I'll tell you how are we going to cover this topic that I have already discussed in my previous two videos. So I'll just take a overlook of this. So we have divided this chapter into four parts. So part 1 is your Werner's theory and important definitions. Part 2, very important, nomenclature and isomerism. You can easily expect one question from these, two questions from these two topics. And part 3, bonding theories, that we are going to do today, is also very important. And then in part 4 we'll be doing metal carbonyls and its important applications. Okay, so yes, now coming to weightage wise, you can know from 2 to 3 questions every year we can expect from this particular chapter. Okay, now coming to the part 3, bonding theories, we have two important bonding theories that we are going to discuss, valence bond theory and crystal field theory. Okay, so now coming to, in crystal field theory we will be discussing about octahedral splitting and tetrahedral splitting. Okay, so this will get clear once we do the topic. So first of all, you have to understand that bonding theories we have two, valence bond theory and crystal field theory. In crystal field theory we have again two, one is octahedral and another is tetrahedral. Okay, so if you remember, octahedral is for coordination number 6 and tetrahedral is for coordination number 4. Okay, now coming to, in bonding theories, after that we'll also be discussing about color of the coordination compounds. Okay, so this we have already discussed in D&F block. So some repetition, or we can say more detail, we can understand in this particular section. Now coming to valence bond theory. So first of all, what does the valence bond theory says? See, according to this theory, the metal atom or the ion under the influence of ligands can use its n-1d, ns or np, or ns, np and nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral or square planar. Okay, so in valence bond theory what happens? 1d, so we can have either n-1d, ns and np. Okay, orbitals can combine, or ns, np and nd. These two sets, either these sets of orbitals or these set of orbitals can combine to give you equivalent number of hybrid orbitals. Now what is the meaning of this equivalent orbitals? So remember, number of hybrid orbitals produced, number of hybrid orbitals, okay, is equal to number of orbitals combined. Okay, this is very important conclusion that you must remember. Number of hybrid orbitals formed is equal to number of orbitals combined. Okay, now these hybrid orbitals are allowed to overlap with the ligand orbitals that can donate electron pairs for bonding. So what is happening? First, metal has these orbitals. Okay, in metals, in the metal itself, these orbitals will, either this set of orbital or this set of orbital will combine to give you hybrid orbitals. Okay, so step 1, if you want to understand, step 1 is orbitals of metals, okay, combine means I can say they undergo hybridization to give hybrid orbitals. Okay, Combines means mix. Okay, so the orbitals of the metal undergo mixing to give you hybrid orbital. Here you have to remember that the number of hybrid orbitals formed should be equal to the number of orbitals combined. Suppose 4 orbitals are combining, then 4 hybrid orbitals will be produced. Now after the hybrid orbitals have been formed, the step 2 is this one, where the hybridized orbitals are allowed to overlap with the ligand orbitals. So now ligands in the coordination compounds, we have coordinate bonds where the ligand will donate the electron. So where the ligand will donate? In the hybrid orbitals of metals. Clear? Okay. Now you can see different for different hybridization what are the geometries. So if coordination number is 4, okay, then we have two types of hybridization. One is sp3, one is dsp2. Okay, so in sp3, if the hybridization is sp3, then the geometry is tetrahedral. If it is dsp2, then it is square planar. Okay, now coming to coordination number coordination number 5, then the hybridization is sp3 and the geometry is trigonal bipyramidal. Now for coordination number 6, okay, coordination number 6, sp3d2 or d2sp3, both the time the geometry is octahedral. Getting? Let us revise. This is very important slide. You must remember, this is very important. Okay, so what I am saying, for coordination number 4, there are two types of hybridization, sp3 and dsp2. For coordination number 6, there is also two types of hybridization, sp3d2 and d2sp3. In our syllabus, we should know the this one, the example and the geometry for coordination number 5, but generally our questions will be from coordination number 4 and 6. Okay, fine. Now going to this one. So here are the compounds that is given in the example in our NCERT book from where questions can be asked. So you have to, I'll just revise this one. So for if CONH3 whole 6 3 plus is there, then hybridization is D2sp3. If D2sp3, then it is octahedral. Okay, so now remember, if the hybridization is D2sp3, so I told you for coordination number 6 there are two hybridization, sp3d2 and D2sp3. So if it is a D2sp3 hybridization, then we call it inner orbital complex. I'll tell you the reason for what. Now if COF6 3 minus, then it is called sp3d2 hybridization, and here the complex is called as outer orbital complex. Okay, now what is the meaning of inner orbital complex? See, if NS and NP is used, right? Suppose here I'll tell 4s and 4p is used. Now if 3d is used in the hybridization, when I write n minus 1 d2sp3, that means 3d orbital is used. Now 3d orbital is present inside of 4s, or we can say towards the nucleus, so it is called inner orbital complex. Now instead of 3d, if in the hybridization we have ns, np and nd, that means 4s, 4p and 4d. If these orbitals are present, then we call it sp3d2 hybridization or outer orbital complex. Okay, now this is, as I told you, these two hybridization will have geometry octahedral. The magnetic behavior of one is diamagnetic, another is paramagnetic. Now that also we will discuss. As you know, diamagnetic means no unpaired electron, paramagnetic means unpaired electrons are there. Now coming to NiCl, now you may be asking how these hybridizations have come, that we will discuss. Okay, now if you see NiCl4 2 minus, okay, here the coordination number is 4 and coordination number 4 has two hybridization, sp3 and dsp2. So if it is sp3, the geometry will be tetrahedral as discussed, and here because unpaired electrons are there, we call it paramagnetic. Now if you see NiCN4 2 minus, it is dsp2, so geometry is square planar and it is diamagnetic. Okay, so you can calculate these values and you can find out, but it is better that you should know at least the hybridization so that you can quickly do the questions. Okay, so these 4 examples are very important because it is given in our NCERT book. So I'll recommend that you should remember these hybridizations for these 4 compounds so that question solving will be much faster. You can save a lot of time because it actually requires a lot of time to find the hybridization, so that much time will be wasted in the exam. So if you remember this only 4 compounds, you can save a lot of time here. Okay, fine. So now we will understand these hybridization, geometry, diamagnetic, how it has come for all these 4 examples in detail. Okay, so now let us first go to cobalt NH3 whole 6 3 plus, right? CONH3 whole 6 3 plus. Now if you see what is the electronic configuration of cobalt, that is 4s2 3d7, right? Then in 3 plus what will be the electronic configuration? 2 electrons will go from here, so I'll write in this way so that it is more clear. 3d7, okay, 3d7 4s2, right? Now cobalt 3 plus, the charge of cobalt is plus 3, 3 electrons will be lost, so 2 electrons from here and 1 electron from here, so I'll get 3d6. So how is this 3d6 present? We have 5 orbitals, 1 2 3 4 5, so 1 2 3 4 5 and 6 electrons are present. Now you see this one, cobalt is forming 6 bonds, right? So I need 6 empty orbitals. So if cobalt, so what is I can say? Coordination number should be equal to number of empty orbitals required. Number of empty orbitals required. So now what happens here? We'll understand once what is strong field ligand and weak field ligand. So you have to remember NH3 is a strong field ligand. Okay, it is a strong field ligand. So if strong field ligand is there, then what will happen? Pairing of electrons will take place. Pairing of electrons take place. Okay, so now what is there? This is your 3d. After 3d we have 4s orbital, and after that we have 4p orbital, right? And I need 6 vacant orbitals. So now since NH3 is a strong field ligand, what will happen? These 4 electrons will get paired up. Okay, so this is the ground state configuration. Now what will happen? In the excited state, these electrons will get I'll say combined, so I'll get like this. We have 3d, 1 2 3 4 and 5, 6 electrons will be present like this. Okay, here we have 2 unpaired electron, and we have 4s one box, and we have 4p another box. Okay, so now you can see how many unpaired electrons we have. We have here how many empty orbitals we have? 1 2 3 4 5 and 6. So these 6 orbitals will undergo what? Hybridization. Okay, so after they undergo hybridization, we will get 6 hybrid orbitals now. Okay, 1 2 3 4 5 and 6. Each of these hybrid orbital name is D2sp3. Okay, each of this hybrid orbital name is D2sp3. So total I got 6 hybrid orbitals, each of the name D2sp3, right? Now what will happen in this compound? Who will come? The ligand. Which is the ligand here? NH3, right? So we'll draw the ligands here, NH3. So NH3 ligands are there. Okay, I can draw one more here. So these NH3 ligands will donate their electrons in the empty orbitals. Okay, you can donate it like this. Okay, so now if this is happening, so what I can say now, the ligand has donated its electrons in the empty orbitals, empty hybrid orbitals of the metal, and the coordinate bond has formed. Now here we have used, so what are the orbitals used here? N-1d, okay, Ns and Np. So I can say 3d, 4s and 4p. So this, because it is using the N-1d orbital, the inner d orbital is used, it is called as inner orbital complex. Okay, inner orbital complex. Okay, now talking about its if you can see any magnetic behavior, now you have to see the magnetic behavior here. There is no unpaired electron. Because it is no unpaired electron, it is diamagnetic. Okay, now for coordination number 6, what is the coordination number 6? For coordination number 6, we know the geometry is octahedral. Hybridization here is D2sp3. Okay, so these are the things that we can understand for this particular compound. Now let us go to our next example, COF6 3-. Okay, so yeah, so now we have COF6 3-. Okay, so here also cobalt, if you write, the oxidation state is, the hybridization is 3d7 4s2. So cobalt 3 plus will be again 3d6, right? So we have like this 5 orbitals, 1 2 3 4 5. So I'll have 1, 2, 3, 4, 5 and 6. Okay. So now what is there? We have 3D. Okay. And we have 4s and we have 4p. So let us draw first. This is 3D. So I have 3D 1, 2, 3, 4, 5 and 6. Okay. Then we have 4s, we have 4p. Okay. Now what happens? In this case, what I can say is important one. Fluorine is a weak field ligand. So if weak field ligand is there, what will happen? No pairing of electrons takes place. No pairing of electron takes place. Okay. So pairing of, so in the previous case what we did, we paired these electrons, right? We cannot pair here because fluorine is a weak field ligand. So if it is a weak field ligand, then what will happen? These electrons cannot pair up, and but we still need 6 empty orbitals because coordination number is 6. So what we'll do? 1, 2, 3, 4 and I need 4d orbitals now. Okay. So 1, 2, 3, 4, 5. So now what happens here? This I need 6, right? Up to this sp3d2. sp3d2. These orbitals will undergo hybridization to give you 6 hybrid orbitals now. Okay. 1, 2, 3, 4, 5, 6. These all hybrid orbitals names are sp3d2. Okay. And who is donating electrons here now? Fluorine will donate the electrons. So I have fluorines here. Okay. And fluorine will donate their electrons in this empty hybrid orbitals of cobalt. Okay. So now if I talk about the hybridization, what is the hybridization now? sp3d2. Okay. And what about the magnetic moment? If I say magnetic nature, you see there is 4 unpaired electrons here, right? 4 unpaired electrons are there. If unpaired electrons are there, then it is paramagnetic. Okay. Now coming to geometry. So for coordination number 6, there is only one geometry, that is your octahedral. Now whether it is inner orbital complex or outer orbital complex, if 4s, 4p and outer d, 4d is used. Outer d is used, so that is why we call it outer orbital complex. Okay. Fine. Now coming to, we'll do 2 more examples, NiCl4 2 minus. Okay. Let us see this one. We have NiCl4 2 minus. So now if I calculate here, nickel oxidation state is, electronic configuration is 3d8 and 4s2. Now if I have nickel 2 plus, so I will have 3d8 only, right? So if I draw the d8 orbitals, so I have 3d, 1, 2, 3, 4, 5. So you should always fill like this, 1, 2, 3, 4, 5, then 6, 7 and 8. Okay. Now this is 3d, then I have 4s and then we have 4p here. Okay. So now you see here the coordination number is 4, right? So that means how many empty orbitals I need? We need 4 empty orbitals, right? We need 4 empty hybrid orbitals. Sorry, we need 4 empty orbitals to undergo hybridization. So we need 4 empty orbitals to undergo hybridization, right? So now if you see what are these, so now again chlorine, as we discussed, chlorine is a weak field ligand. If weak field ligand is there, then what will happen? No pairing of electrons will take place, right? So again, but still we will need 4 empty orbitals, so we can consider 1, 2, 3 and 4 empty orbitals. What will happen here? These 4 empty orbitals will undergo hybridization, sp3. So what I'll get? I'll get 1, 2, 3, 4. 4 empty orbitals have undergone hybridization to give you sp3 hybrid orbitals. Okay. So now what will happen? There is a ligand, this one, Cl is there, right? So these Cl will donate their electrons here. Okay. These Cl will donate their electrons here to form a coordinate bond. Okay. So now what is there? We have Ni. Now if I talk about the properties, hybridization is what? Hybridization is sp3. Okay. Now about talking about the magnetic behavior, you can see any unpaired electrons. So how many unpaired electrons we have? 2 unpaired electrons are there, so that is why this is paramagnetic. Okay, next coming to geometry. So for coordination number 4 we have two geometries, like two hybridizations, sp3 and dsp2. For sp3 the hybridization is your tetrahedral. Okay, clear? Now in the hybridization there is no d orbital used, so there is no inner or outer complex. That inner orbital and outer orbital theory is valid for coordination number 6. Okay, coordination number 4 we have only the hybridization, magnetic nature and the geometry. Clear this one? Now we'll go to the next example, that is NiCN4 2-. Okay, so now what happens here? If we see the nickel electronic configuration is what? Here 3d8 and 4s2, right? Then if I have Ni2 plus, then it will become 3d8, right? So I have this one 3d8. So 1, 2, 3, 4 and 5. So 1, 2, 3, 4, 5, 6, 7 and 8. Then we have 4s. Okay, and then we have 4p. Okay, now what will happen here? When this is present, there will be a, what I can say, there will be pairing of electrons. Now why there will be pairing of electrons? You have to remember here Cn is a strong field ligand. So that is why what happens? Pairing of electron takes place. Pairing of electron takes place, right? So now if pairing of electron takes place, this, so okay, how many empty orbitals we need? See, coordination number is 4, so we need 4 empty orbitals. We need 4 empty orbitals, right, to undergo hybridization. So if this one comes here, pairing takes place, so what I'll get? I'll have 1, 2, 3, 4, 5. So 1, 2. Okay, so we'll get, this is the configuration. Okay, and then we have 3d, 4s and 4p. 4s and we have 4p. So now what will happen? This, okay, this 4 orbitals will undergo hybridization to give you dsp2 hybridization. Okay, so in dsp2 hybridization what will happen now? 4 new orbitals, or I can say 4 hybrid orbitals are formed, and each hybrid orbital name is dsp2. Okay, so now what will happen? There is Cn here, Cn, Cn and Cn. So these Cn will donate the electrons here. Okay, this Cn will donate its electron here to form a coordinate bond. Now talking about this one, so what we have done, what is the hybridization? We'll talk about the magnetic properties and we'll talk about the geometry here. So if you see, the hybridization is what? Hybridization is dsp2. Okay, magnetic property, we cannot have any, and we don't find any unpaired electrons here, so it is diamagnetic, right? And then if you see geometry, it is, because dsp2 hybridization is there, the geometry will be square planar. Okay, so remember, in case of coordination number 6, there is only one geometry. Whether the hybridization is sp3d2 or d2 sp3 doesn't matter, the geometry will still be octahedral. But in coordination number 4, there are two types of geometry, that is square planar and there is tetrahedral. So if it is dsp2 hybridization, then it is square planar. If it is sp3 hybridization, then it is tetrahedral. Okay, so yes, so that's how we are done with 4 examples. Now let us solve some questions. Okay, the coordination number of copper in the complex formed by adding excess of ammonia in the copper sulfate solution. So if we add excess of ammonia in the copper sulfate solution, okay, so the reaction takes place like this. Copper reacts with 4 ammonia molecule. Okay, so now you may ask, like, ma'am, how do you know that it reacts only with 4? So that is the example given in your book. So copper with ammonia forms takes 4 ammonia and we get this type of complex. So what is the coordination number here? So coordination number of copper will be 4 here. Okay, so this reaction you have to learn. Okay, Now coming to next question, the complex ion which has no d electron in the central metal atom, it should not have any d electron. Okay, let us check now. If you see what is the oxidation state of manganese in option number A, see this is X, this is so I can say X, then -8 is equal to -1, so I can say X is equal to +7, right? So if I calculate, manganese electronic configuration is 3d5 and 4s2, right? So if we have manganese +7, argon is present, okay, argon is present here also. Now these 7 electrons will go, so we will get only argon. So this can be answered because it has no d electron in the central metal atom. Now if you talk about this cobalt, here NH3 is a neutral field ligand, so cobalt oxidation state is +2. So if I go for this example, okay, cobalt oxidation state is +2, so that means we have argon +2 state 3d7, right? So there are some d electrons, so the correct answer for this question will be option number A. You can check for these two options as well, okay. Now coming to next question, which one of the following complexes is an outer orbital complex? So here I'll tell you two things you have to remember. For outer orbital, okay, outer orbital we need generally weak field ligands, and for inner orbital complex generally we need strong field ligands, okay. But remember, this is generally, okay. Sometimes with strong field ligands also we can get outer field configuration. I'll tell you the example for that also, but this is generally what happens. Now if you see which are the strong field ligands, so we need outer orbital complex, right? Now if you see outer orbital complex, so for that we need weak field ligand, but here all are strong field ligands, okay. I'll give you the list of which is strong field, which is weak field once we go for crystal field theory. Then how can we check here? Okay, so now let us check one by one example. MnCN6, so that is manganese oxidation state is +2, right? So manganese oxidation state is +2, so that means we have 3d5 orbitals here, right? 1, 2, 3, 4 and 5. So we need 6 unpaired electrons, so we can, this will undergo pairing. So this one will have D2sp3 hybridization, right? Because these two can undergo pairing here, and we can get 2 unpaired electrons, 2 vacant orbitals to get D2sp3. Now cobalt we have already seen, it is D2sp3. Now let us check about nickel first. Okay, nickel, if you see, it is nickel configuration is, see, 3d8 4s2, and here it is nickel 2 plus, so I'll get 3d8, that means 1 2 3 4, so 1 2 3 4 5 6 7 and 8, right? So now what happens, see, we need 6 empty orbitals, okay, and the hybridization is either D2sp3 or it is sp3d2. That means if we are using inner d orbital, we need 2 empty orbitals from in d orbital, right? If we are using the 3d orbital, then we need 2 empty orbitals in this one. But if I do pairing here, okay, if in this one if I do pairing, then what I'll get? 3d 1 2 3 4 5, so I'll get, if I do pairing, I will be left with only 1 empty orbital, right? But that is not of any use, because if we want to get D2, so coordination number 6 has only 2 hybridization, D2sp3 or sp3d2. If I want D2sp3, then I need 2 empty orbitals, but after pairing also I am not able to get 2 empty orbitals, right? So in that case what happens, there is, so I can say that here there is no use of pairing. There is no use of pairing. Now why there is no use of pairing? Because we are not able to get 2 empty orbitals, so that is why here pairing will not take place, and we will get the, so this one there will be no pairing, this will be as it is, and we will use 4s 4p and 4d for hybridization, okay. So this you can see, I told you, that is why I mentioned use generally. Here you see, even though NH3 is a very strong field ligand, but still here we cannot have inner orbital complex because of the electronic configuration of nickel. So the correct answer for this question will be option number D. Okay, this is an important question here. Okay, now moving forward, which of the following is D2sp3 hybridized? Okay, Now if you see D2sp3 hybridized, so we need 2 d orbitals, right? 2 empty d orbitals. For COF6 we already know it is sp3d2, right? This is not the answer, and if this is not the answer, then this cannot be the answer, right? Now let us check for these two. If you see FeH2O, okay, now you have to remember one thing here important, that water, okay, water is a weak field ligand, but with cobalt 3 plus it behaves as a strong field ligand. Okay, this is very important, you must remember. Okay, with cobalt 3 plus water behaves as a strong field ligand. Now if I see this one, cobalt electronic configuration 3d7 4s2, here I will get 3d6, right? In cobalt plus 3 state it is 3d6. So if I see like this, I have 1 2 3 4 5 and 6. So I told you with water with cobalt 3 plus water behaves as a strong field ligand. So what will happen? Pairing of electron will take place. So I will get like this. Okay, so 1 2 3 4 5 6, this is 3d6. Okay, now here we have these d orbitals available, 4s and 4p, 4s and 3 4p, right? So now D2sp3 is available here. Okay, so now we can say that for cobalt plus 3 the hybridization is D2sp3. The correct answer for this question will be option number B. Okay, but remember generally water is a weak field ligand, but with CO3 plus it behaves as a strong field ligand. Okay, next coming to, okay, which of the following complexes is paramagnetic with D2sp3 hybridization? Okay, it is paramagnetic but it is having D2sp3 hybridization. Okay, let us check now. If you see FeCN6 3 minus, Fe charge is plus 3, right? So I will have 3d5 configuration, right? Now if I have 3d5 configuration, you can see here we have like this 3d5, so 1 2 3 4 5. Now what happens, because Cn is a strong field ligand, pairing of electron takes place, but I need only two empty orbitals, right? So what will happen here, these two will go and undergo what I can say, pairing of electrons will take place. So if pairing of electron takes place, then what I'll get, I'll have 1 2 3 4 5. So these two electrons will paired up and we have like this one. So I'm getting 2 empty orbitals, right? 2 empty orbitals I'm getting, but still I have 1 unpaired electron here. So that is why this one will be a paramagnetic complex. Okay, so correct answer for this question is option number A. Okay, so let us see the next question. The magnetic moments of the complexes given below are in the order. So if you want to calculate the magnetic moment, we need to calculate the number of unpaired electrons. If number of unpaired electrons is less, magnetic moment will be less. If number of unpaired electrons is more, magnetic moment will be more. So the compounds given are your NiCO4, NiCl4 2 minus. Okay, see here is a small mistake, that is this is CrNH3 whole 6 2 3 plus. Okay, so this compound please change, it is CrNH3 whole 6 3 plus, and then we have COF6 3 minus. Okay, so now you see if nickel is there, it is a neutral compound, so nickel oxidation state is 0 here, right? So electronic configuration is 3d8 4s2, so that means we have 3d8 1 2 3 4. So 1 2 3 4 5 6 7 and 8. Okay, and we have 4s2 here. So now cobalt is a very strong field ligand, sorry, CO is a very strong field ligand, it undergoes pairing of electrons. So what will happen, these two electrons will undergo pairing. Okay, so now what I will get here, we will have 1 2 3 4 5. So 1 2 3 4 5 6 7 8 and 9 10. So no unpaired electrons, that means N is equal to 0 here. Now if you see Ni, so if you see that means 0 means magnetic moment has almost become 0. So that means 1 has to be the least one. So we can say there is this option 1 is highest, right? So only one option is there where 1 is lowest. So this has to be the answer. But we can check the other options also. So if you see here, nickel oxidation state is +2, right? That means 3d8. So if I draw the electronic configuration here, 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7 and 8. Now if you see here, chlorine is a weak field ligand, there is no pairing of electrons, so we will have 2 unpaired electrons here, so N is equal to 2. Now if you see CrNH3 whole 6 C3 plus, so chromium electronic configuration is 3d5 and 4s1. So chromium 3 plus means what? We will have 3d3, right? So now I have this one, 1, 2, 3, 4, 5, 1, 2, 3, right? So 3d3 is there. Now you see NH3 is a strong field ligand, but NH3 does not have to do any pairing here because already 2 empty d orbitals are available, right? So there is no pairing of electrons takes place, so N is equal to 3 here. Now COF6 we have already seen, N is equal to 4. So as the number of unpaired electrons will increase, magnetic moment will increase, so the correct answer for this question will be option number B. Okay. Fine. Now going to the next question, which of the following compounds is not colored? Okay, so for colored of or not colored, we need to check that there should be unpaired electrons. Okay. For color, for a compound to be colorful, it should have unpaired electrons. The question is asking not colored. Not colored means it should not have any unpaired electrons. So now when you see, you should remember that zinc is a compound which is not having any unpaired electron and it is colorless compound. So that is why here also if you see the zinc electronic configuration, Zn is in +2 oxidation state here. Its electronic configuration is 3d10, no unpaired electron, so that is why this compound will be colorless. Okay. Now coming to, okay. So now we'll go to the next theory, valence bond theory we have done. Next theory is your crystal field theory. So if you see here, in crystal field theory, what happens? The metal and ligand bond, okay, is considered to be ionic in nature, okay, and there is electrostatic interactions between the metal and the ligand, okay. Now when the ligand approaches the d orbitals, split to reduce the repulsion. So there is, see, in metal there are 5 d orbitals, okay, and all the 5 d orbitals have equal energy. We call it them as degenerate orbitals, means they have equal energy. Now when the ligands approaches the metals, okay, these 5 degenerate orbitals undergo splitting. Okay, now splitting of d orbitals depends on the strength of the ligands and the whether it is octahedral field or tetrahedral field. On these two factors, the splitting of the d orbital depends. Okay. Now coming, this is very important, this is your spectrochemical series. Okay, here what happens, spectrochemical series, it tells you about the strength of the ligands. So I'll remember, you have to remember certain ligands here, NH3, Cn minus, CO, En, these are strong field ligands. H2 and below, these all are your weak field ligands. Okay, I minus, Br minus, Sn minus, Cl minus, S2 minus, F minus, OH minus, C2O4 2 minus, H2O. Okay, these up to H2, these are your weak field ligands. Then after OH2, whatever is there, this is your strong field ligand. But you have to remember, water with cobalt 3 plus behaves as a strong field ligand. Okay, this exception you have to remember. Okay. Coming to next one, so crystal field theory will study in 2 parts, coordination number 6 and coordination number 4. Coordination 6 means when metal is there, okay, and ligand approaches from 6 sides. The ligands are coming from the 6 sides. Then what will happen? The d orbitals of the metal will split, but the splitting will be in such way that 3 orbitals go down. Okay, and these 3 orbitals we call it T2G. Which 3 orbitals go? DXY, DYZ and DZX. Okay, and 2 orbitals go up, which we call them as EZ, DZ square and DXY, DX square minus Y square. Okay, now from here, this energy level, this energy, how much down it has gone? It has gone by minus 2 by 5, and this energy has increased by plus 3 by 5. Okay, these also you have to remember. So now you see, when all the 5 d orbitals were there, when the ligands are approaching, initially the energy of the d orbital will increase. When they come very close, the d orbitals will split in this way, in case of what? Octahedral splitting only, in the coordination number of 6. Okay, now what happens? Now we have to know the electronic configuration. Now see, if it is a weak field ligand, the splitting will be less. If it is a strong field ligand, splitting will be more. Okay, so now suppose this is d orbital. See, yeah, Okay, now see, suppose this is your 5d orbitals. Okay, 1 2 3 4 5. Now if it is a weak field ligand, okay, so the splitting will be just like this. We will have here T2G and here we have EG. Now if it is a strong field ligand, okay, then the splitting will be, the gap between the two layers will be more. This is T2G and we'll have EG here. Okay, clear? Now we have to understand the electronic configuration. Now suppose D1 is there, okay, in the d orbital there is one electron is there. So whether it is strong field or high field, what will be the configuration for D1? There will be one, whether if it is a strong field also it is like this, if it is a weak field also it is like this. So the configuration for D1 becomes T2G1. Okay, now if it is D2, here also it can be either in this way or it can be this way, both the configuration it is same. So for D2 the configuration is T2G2. Okay, now if it is D3, here also it can be D3, here also it can be D3, doesn't make any difference. For D3 it is T2G3. Okay, now when it comes D4, this is very important. Now D4, see, in the case of this one, the fourth electron has a chance of either pairing here or going to the higher level. Similarly here also it has a chance of getting paired or going to the upper level. Now see, suppose, just imagine you are in a house, okay, there is 3 rooms in the ground floor and 2 rooms in the first floor. Okay, 3 rooms in the ground floor and 2 rooms in the first floor. Okay, so what I am saying, just imagine we have a house, we have 3 rooms in the ground floor, okay, and 2 rooms in the first floor. Okay, now suppose these 3 rooms in the ground floor are already occupied. Okay, suppose you are going to a hostel or something, you imagine like that. These 3 rooms in the ground floor is already occupied. Now you can have a single room in the first floor, or you can have a sharing room here where the people here are not very good, or you are having repulsions between them. So what will you prefer? Obviously you will want, okay, it is only first floor, right? So that is not, in lift is not there. Okay, imagine lift is also not there. So you will think that, okay, this is only first floor, I can stay like peacefully in the first floor, and it is also not very difficult for me to to move from ground floor to first floor. It is very easy to commute. So definitely I will prefer to go for first floor where I can live peacefully, and also my life is not difficult because it is only first floor. I do not have to do much climbing every day. So here that is the case. So the fourth electron here goes here. The fourth electron says, okay, why I should undergo repulsion between these people. The next energy level is not very high, so I can go and sit there peacefully. So the fourth electron goes here. Now suppose the same case is there. Here what happens now, this one, okay, here the another empty room is available, but it is in the 21st floor. Okay, the 21st floor there is one single room is available for you, and there is no lift for you. So every day you have to climb that much, and you have to climb down every day that much. So what will you prefer? Okay, who will do every day this much climbing? Let me settle with this person who is in the ground floor. Let me settle there, let me adjust there. You will think like this. So the electron also sees like that, who will climb this much, who will go to the very high energy level. So let me adjust here. Okay, so now what happens, see, in the strong field ligand, because the energy gap is very high, okay, this is first floor, this is ground floor, then this is 21st floor, very high, the electrons become lazy to go to the higher level. They think, let me adjust here. Okay, so now what happens for D4, okay, for D4, okay, for D4 if it is a weak field ligand, then what will be the configuration? It is T2G3 EG1. But if it is a strong field ligand, what will be the configuration? T2G4. Are you getting? Just imagine ground floor and 21st floor is there. Electrons will be very lazy to go to such a high level of energy, so they try to prefer pairing in the lower level where there is energy is less. Okay. But in case of weak field ligand, because it is not a very difficult job, electrons say, okay, let me just go to the first floor and rest there peacefully, because that is a single room, I can live peacefully there. Okay, that is how it happens. Now coming to D5 configuration. D5 also, see, one more electron is there, one more level is here, so D5 also will try to go there. Here also same thing, it cannot jump that much, so it will pair up here. So for D5, if we have weak field ligand, okay, then I'll get T2G3 and EG2, and for strong field ligand I will get T2G5. Okay, now if you see D6, now see for D6, here it's already, here also all the rooms are occupied, here also all the rooms are occupied. So why to climb there and stay with someone which already like stay with repulsion? Why to climb every day? Anyway I have to stay with repulsion. So the 6 electron will definitely try to come here, because here also there is repulsion, here is also repulsion. Why not there be in the ground floor every day? At least the electron did not climb to the first floor, right? Thinking in that way, 6 electron will come here and settle down. So for D6, what will be the configuration? In the weak field ligand, it is T2G4 EG2. Okay, in strong field ligand already that is very high, so it will go here. So we will have T2G6. Okay, now coming to D7. D7 also same, for anyhow it has to share the room, so why to share in the first floor? Let us share in the ground floor only. So for D7, if you see weak field ligand, it will become T2G5 EG2. Now if you come to strong field ligand, now see, all the ground rooms are already occupied. There is no other empty place. There is, you came late, you joined your admission late, there is no other room, you have only the 21st floor free for you. So definitely the only option left for you is you have to go there and settle down, right? So that is why the 7th electron here goes to EG level. So what I'll get here? T2G6 and EG1. Okay, now coming to D8. So if I see D8 configuration, already 6 electrons we have done, 7th electron, 8th electron also same thing, these two are occupied, it will occupy here. So I will get T2G6 EG2, and here also you say 6 already occupied, 7th and 8th. So same configuration will come for D8. D9 also will get T2G6, okay, then 9th electron will come here, EG3. And here also it will come here. Now D10 will be T2G6 EG4. Here the 4th electron will come, and here the 4th electron will come. So now you have to remember that for D1, D2 and D3 and D8, D9 and D10, the configurations are same. So I will erase this one, it is, one second. Okay, so you have to remember that for D1, D2, D3 and D8, D9 and D10, strong field, weak field configurations are same. But for D4 to D7, that is D4, D5, D6 and D7, the configurations are different in strong field ligand and weak field ligand. Okay, so now how do we represent strong field? See, in strong field what happens, the delta O, this variation in energy is called as delta O. Okay, delta O is a difficult thing, and for electron also pairing is also difficult. To climb also it is difficult, and it is difficult to adjust with another electron and get repulsion. But which one is more difficult? Climbing the EG level is more difficult. So in this case, in strong field ligand, we say that this delta O is greater than the pairing energy. Here pairing energy is there, the electron has to pair and has to suffer, but this suffering is less than climbing to the 21st floor. Okay, so we write this one as delta O is less than P. Now here what happens, here you see this is also delta O, okay, but here the electron feels that it is better to climb. Okay, delta O becomes like climbing is easier than adjusting with another electron with repulsion. So here what happens, we write delta E is less than P. Okay, pairing energy is more here, pairing energy is less here. So you have to remember these two terms also, questions are asked from here. For strong field ligand, delta O is greater than pairing energy. For weak field ligand, delta O is less than the pairing energy. Okay, fine. Now you can see the splitting in the tetrahedral. Tetrahedral means what? Metal is there and ligand approaches from 4 sides. In coordination number 6, ligand approaches from 6 sides. So now what happens here? there is a degenerate 5d orbitals are there, their energy is lifted, 5d orbitals are there, then here there is 2 orbitals and here there is 3 orbitals. So here this is E and this is T2, E here and T2 here. Okay, so we will have dz square and dx square minus y square, and here it is dxy, dyz and zx. Okay, so the splitting here, here always there is you should like here always there is like if you fill d1, d2, okay, next d3, d4, d5, then d6, d7, d8, d9 and d10. Okay, so here you remember there is no G is used, E and T2 is used only. Okay, fine. Now coming to the color, so we have already discussed this in the D block elements also. The electrons in the lower level gets excited to the higher level, and then when they come back they release energy in the visible region, because of which we can find the color. Okay, now the color observed is corresponding to the complementary color of the light. The frequency of the light absorbed is determined by the nature of the ligand. So if there is a very high strong field ligand is there and the splitting is more, then we need a light of high energy where the frequency is more. Okay, so here you should remember color of the compound, the complementary color theory. So if we have V, B, G, Y, O and R, if the color is absorbing violet, if the compound is absorbing violet color, it will be visible as yellow. Blue if it is absorbing, orange it will be visible, green if it is absorbing, red it will be visible. So whichever the color is absorbed, the complementary color of it will be visible. Okay, fine. Now coming to the next one. Okay, which of the following ligands has the highest delta O value? So if the ligand is very strong, splitting will be very more and the delta O value will be highest. So if you have seen the spectrochemical series, Cn minus is a very strong field ligand. So correct answer for this question will be option number D. Okay, next, if delta O is less than P, if delta O is less than P, that means which one this is? Weak field ligand. Okay, we have weak field ligand, very less difference. Okay, weak field ligand. That electronic configuration for D4. So we will have 1, 2, 3, very less difference. The electron will not try to share rooms here, it will come here. So what will be the configuration? T2G4 and T2G3 EG1. Correct answer for this question will be option number B. Okay, next, okay, now we'll do some practice questions from the previous year papers, and before that I'll discuss this question which I gave you as a homework in my previous class, that is isomerism. So if you see here CONH, so this is of type ML4A2 type, right? Okay, so now there is NO2, so definitely it will show linkage isomerism. So here there is no linkage isomerism, we can eliminate this option. Now if it is ML4A2 type, we will have cis and trans, so that is why it will also show geometrical isomerism, and here also geometrical isomerism there. Here there is no geometrical isomerism, so we can eliminate this option. Now coming to ionization isomerism, if you do put it in water, this one will show one ion, or they can have a ionization isomer also where different ions will be produced. So the correct answer for this question is option number C. So here there is no optical isomerism. If you have remember, we have optical isomerism for two types, that is MLL3 or we have MLL2 and A2. If these two type of compounds are there, then we will have optical isomerism. Okay, fine. Next, coming to the PYQs, which of the following system in an octahedral complex has maximum number of unpaired electrons? So if you see D9, so I told you high spin, low spin is applicable only for D4 to D7. In D9 there will be only one unpaired electron, in D9 if I do 6, 7, 8 and 9, there will be only one unpaired electron. If D6 low spin, we will have the configuration, you can draw it. See, if we have this one, okay, D6 low spin means there will be pairing of electrons here, right? Pairing of electrons will take place here, so there is no unpaired electron. D4 low spin, so if you see D4 low spin, then low spin means again pairing of electron will take place, 1, 2, 3, 4. Okay, high spin and low spin I forgot to mention, see here, 1 second. Okay, so this side if pairing of electron takes place, that is called low spin. Okay, and if there is no pairing of electron takes place, we call it high spin. Okay, please remember this one. Pairing of electrons where we are doing strong field ligand, that is called low spin, and where there is no pairing of electrons, weak field ligand, we call it high spin. Okay, so that is what is given here in the question. Okay, high spin means for D9, for that is applicable again only for D4 to D7. D9 anyway 1 electron. D6 low spin means strong field ligand, pairing of electron takes place, number of unpaired electrons will be 0. D4 low spin, again pairing of electrons takes place, so number of unpaired electron is 2. Now D7 high spin means weak field ligand. Weak field ligand means no pairing of electrons. So what will be the configuration here? So we have 7, right? So we will have 1, 2, 3, 4, 5 and then 6 and 7. So number of unpaired electrons here is 3. So the maximum number of unpaired electrons is in option number D. Okay, fine. Next question, crystal field splitting. Energy of cobalt is 18,000. The crystal field splitting of CoCl4 is this much. So if you see, there is a relation between delta T is equal to 4 by 9 of delta O. This is tetrahedral splitting and this is octahedral splitting. Okay, so we can write it like this. This formula, please remember, important formula. Delta T is equal to 4 by 9 of delta O. So now if I calculate, I need to calculate tetrahedral splitting. Here you can see coordination number is 4, so this is a tetrahedral, and here you can see coordination number 6, so it is an octahedral. So that is equal to 4 by 9 of delta O. So that is equal to 4 by 9 of 18,000. Okay, so that is equal to 8,000 centimeter inverse. So the correct answer for this question is option number A. Okay, fine. Next, for the crystal field splitting in the octahedral complexes, the energy of the Eg. So we have, remember, in octahedral what I told you, if this one is there, okay, T2G and Eg, right? So the energy decreases by 2 by 5, minus 2 by 5 and increases by 3 by 5, right? The energy of the Eg level will decrease. So this is wrong. The energy of Eg orbital increases, right? This is T2G and this is Eg. Here it is written Eg will decrease. So we can eliminate this statement. Next, energy of Eg orbitals will increase, that is correct, by 3 by 5, and the T2G will decrease by 2 by 5. This statement is correct. So correct answer will be option number option number B. Now if you see here, the energy of the Eg will increase by 3 by 5, that is correct, and T2G also increase. This is wrong, T2 will decrease. Now energy of the Eg will decrease, so that is also wrong, energy of the Eg will increase. So this statement is also wrong. Correct answer for this question will be option number B. Okay, next, the correct order for wavelength of the light absorbed in the complex ions is. So now see, for light absorbed, okay, we need to know the strength of the magnetic strength of the ligands. If ligands are very strong, then there will be more splitting. If more splitting is there, then we need more energy light. Okay, so if you see here, there are 5 NH3 and 1 Cl. Here there are 6 NH3 and here there is 6 CN. So all of you know CN is the strongest ligand, like CN minus is the strongest, after that CO is there, right? So CN compared to these all things, CN is a very strong ligand. So here the splitting will be maximum, energy of 3 will be maximum. I am talking about energy, right? Energy of 3 means in case of option number 3, the splitting will be very high. Okay. Next, coming to here, there are 6 NH3, so next splitting will be 3, and here there is 5 NH3 and 1 Cl, so it will be next. This is energy. Now we know that E is equal to Hc by lambda, or I can say that E is inversely proportional to lambda, right? So what will be the wavelength then? 3, 2 and 1, right? So we have, or I can say 1, 2 and 3, right? So wavelength order will be option number A. Okay, this is very logical and tricky question. Okay, now coming to the last question, the complex having the minimum magnitude. For minimum magnitude we need weak field ligands, and we know chlorine is out of these 4, chlorine is a weak field ligand, so here the splitting will be less, delta O value will be minimum. Okay, So yes, now this is a question for you to practice which of the following complex is paramagnetic. Okay, so you have to just draw their valence bond diagrams and you have to check whether it is having unpaired electrons or not. Okay, so this is a homework question that you have to practice. So yes students, with this we have completed one of the most important topic of coordination compounds, that is bonding theories. So if you have any doubt in these concepts or in these questions, please comment down, I'll definitely address it. Hope you are enjoying learning with me, you are enjoying daily studying with me and practicing these questions. So remember, our target is to hit that perfect 60 score in KCET Chemistry 2025 examination. So if you are liking this channel, if you are liking these videos, if you are liking this course, then please subscribe the channel for more such videos. Okay, thank you for watching. See you soon in the next class and all the very best for your KCET preparation.